So our second speaker today is actually representing the group who submitted the paper. This is Michael Eagle. And now that you're ready to roll, go ahead. Thank you.
So hello, Behrooz was not able to make it to the conference, and so he emailed me and asked me to present the paper. So I'll do that. I'm pretty familiar with some of it, so should be smooth. But anyway, this is work that Behrooz and Tiffany are doing at North Carolina State University, and the idea is to have a data-driven proficiency model. And so the idea here would be able to use like previously collected data in order to determine what new students who are coming into the system, what their level of proficiency is. Are they like a high skilled student or maybe a lower skilled student, in terms of what types of questions we want to offer them. So Deep Thought is a logic tutor. So it teaches how to do proofs in logic, and this is used in computer science courses, teaching discrete mathematics. That's also has been used in argumentation courses for philosophy students. And in the past, we've done a lot of work on this, and one of the things that we did was have some expert-authored decisions relating to how important certain rules were versus other rules. And so the goal here is can we take the expert out of that step so that experts don't need to rank the rules, and we can just use data to determine that. So this is what the new Deep Thought looks like if anyone has seen the older version. So new Deep Thought is used in a web browser. It's built in JavaScript, and so in this sense, it's kind of an updating of an older technology, but it also gives us the ability to do a lot more changes, like implement these things. And so the basic way that you use the system is to, I don't really have a pointer, but to use the rules that are in the middle. So these are going to be your kind of logic axioms like modus ponens, modus tollens, and you will select the certain givens in the left hand on your guy's side, and so in the left side, you'll select those in order to derive new features or new propositions, and you'll use those to eventually solve and find B in this example. So this example is using the old Deep Thought, but I just wanted to give an idea of step one, you start out with really nothing connecting, and your goal is to somehow connect to the conclusion, which is at the bottom. You can see that the first thing that they did there was use simplification to get not W out of the proposition for Z and not W. And likewise, there's some ability to work backwards, so from the conclusion up. And so this is more or less how the system works. So Proficiency Tracks, the idea here was to add some individualization a little bit, but rather than like generating new problems at every step of the way, to start off is to have there be different tracks where some of the problems are considered harder or more challenging than others, and so so everyone starts off and they have the same three problems. So this is what the P1, P2, and P3 means. So this is going to be kind of like level one. So there's the three problems that you have there. Then using your performance inside of those problems, we will put you on a track, or the algorithm will put you on a track that's either a higher track or a lower track. You can see that the difference between the higher track and the lower track is that there's less problems on the higher track, and that's because the problems are more complex. So the same overall knowledge components or same overall content is included and required to go through. It's just that it's done in less problems. The idea is that students who are having difficulty might like to have the problems kind of broken down into smaller chunks. Okay, so just to see if this thing actually does work. All right, so the idea behind the previous iteration of of moving towards this goal is data-driven mastery learning. So we'll say DDML. And so what we do for data-driven mastery learning is we take exemplars. So these are students who have completed all of the problems in the past. So these are going to be, some previous data. And then we, collect their performance, at each one of those cutoff points of when the system would decide whether to put someone on a high path or a low path. And we're doing knowledge tracing on all of the different axioms. So we kind of use the base component of like modus tollens. And so there'll be a score that we have that is how well do we think the student knows, modus tollens as a whole. And so that's what's being tracked here. And so then we've got this essentially like a number, a probability that the student knows the skill at each one of those timestamps. Then we take the average of the KC level for the students at these timestamps. So maybe someone has, 0.46 on KC1 in level 1, and they have a 0.26 for KC2 at level 1. And so we've got that average, and then we place students based on how they fare to that average. So when we collect a new student, we say, okay, well, if your scores are above average, then you go on one track. If they're below average, then you go on another track. Although it might not be exactly like above or below average, but it's using those numbers to decide. So one of the things that is also included in DDML is there's expert-authored rule priorities. So the idea is each one of these problems, some of the rules are the ones that the professor would like the student to be working on. So when they create the problem, it was the intention that they would use these certain axioms. Although with logic, there's definitely a lot of ways to work around that. So some students, can solve a problem by doing something that's not necessarily the way that the professor would want it. And so in order to kind of address that concern from the instructors, we used these kind of basic priorities. So if the rule is not a focal point, it's a 0. If it is a focal point, then it gets a 1. And then if it's somewhere in between, then it's 0.5. And so these priorities were used to decide how to weight those averages before in order to determine where a student should go. With the idea being, just because they have a really high proficiency with something, if that was not something that was considered valuable by the instructor, then we wouldn't want that average to push students down into the other paths. So data-driven proficiency will be the idea to remove that step of needing the professor to or the instructor to come up with these kind of arbitrary 1, 0.5 or 0 things, because we're never really satisfied with that solution. That was just what we used at the time. And so a lot of the inspiration here is to kind of continue on the path of figuring out some data-driven ways to simplify creation of these tutors, or to at least implement different types of feedback for these different tracks. And we wanted to see is a way that might give us better accuracy, or maybe better or different interpretations. And one of the things that we end up using is some cluster-based classification, which I'll get into in a moment. So for data-driven proficiency profiling, or DDPP, we have the first step that we do is we take all those scores that we had before, so all those KC scores, and instead we're going to use a hierarchical clustering in order to determine a group set of bins or clusters of people who have this similar KC score. Then we do that for each rule. Then we take those exemplars, so those people, and we assign them a bin for each rule. So instead of that being the score anymore, we just take which one of these clusters is that student in for each one of the different KCs. And I guess one of the reasons why the term strategic behavior here, what that really is going to mean is some students do have preferences for certain rules. So there's a certain set of axioms that they kind of fall back on, or that they are more likely to use. And so the strategic behavior that we'd be capturing here is if there is a group of students who really is focusing on using a subset of the rules instead of maybe using a little bit of everything, then they should be captured into different clusters, and so that kind of gives a ability for the students to be doing some for us to find them or treat them differently. So after this, the next step, and this uses PCA. So again, we're still going to come up with that weighting score from before, the one that was originally just kind of arbitrarily decided at 1, 0.5, or 0. So now instead, we'll use the importance by taking all of the rule bins for each one of these exemplars, and then taking the PCA weight for that and using that in place of the previous number. So again, this just says, well, if you are this, or if your KCs were binned in this kind of way, so this kind of creates like a template type of student or something, then these are the rules that should be important for you. So that's going to be kind of the big add to this work is now instead of us saying, well, this is the way that you should be solving the problems, we are now kind of saying, well, there could be multiple ways, and depending on which one of those ways you focus on, that should be what determines your proficiency and whether you should go on the high or the low track. Yeah, I just explained that. So for the evaluation portion, we kind of want to track the prediction accuracy. So in this case, we're saying, well, we decided that you were on a certain track. After you completed that level, did we change our minds, essentially? So the idea that that changing a lot would be bad. So if there's more changes, then that's not, then the path that were put on wasn't correct. And so the accuracy measure is going to be based on, did they change tracks? And so this is comparing the difference between the DDML, which is the previous system, and the DDPP, which is the new system. I think DDML is the orange, and then we have blue for DDPP. And for the most part, there's not really a lot going on here. They're pretty similar, but there's no really big differences. So in this case, we kind of get that it's not, it's, at least it's not a lot worse, but it's not necessarily that we're seeing like a huge accuracy shift here. At least not with this type of metric for figuring that out. However, we do see some differences in student dropout. So we've got, this is the old system here, which has dropout occurring at certain level breaks, while in the new system it doesn't occur until pretty much the last level where there's actually any dropout at all. But for the most part, we have a lot more completion. So in that sense, we are seeing some evidence that it might be helping students by getting them into the correct, getting them onto the correct path. So again, there's kind of a couple of advantages. The biggest one being that we don't have to go poll experts every time we have a different question and really decide how important is this rule to this problem, especially when the expert might have a really specific way that they think about the problem, and so there might be like an expert blind spot or something. The other thing is it does provide the ability for there to be alternative strategies to problems, and you don't have to get kind of gated into only one, which is nice. So overall conclusions, we were able to accurately calculate student difficulty track placement, and this is in practice. And students who use this had a comparable dropout rate, if not maybe a little bit better, although it is definitely a little bit difficult to tell, without getting more data, because whenever you see like 100% completion rating across the thing, you always have to think, maybe you need to get some more data too, just to make sure. So future work is, of course, get more data, but also further the implementation of this into the system, so that we get students on these tracks when they're part of the course instead of just during limited studies. Also, more diverse data is going to be necessary for figuring out some of the differences in how it's placing the students on those tracks. Are there any questions? All right.
Let's thank our speaker, and I'll take some questions. All right. Who would like to be first? Question? I have one, if you need time to think. So near the end, you were talking about evaluating these methods by looking to see who changes tracks. And the conceptualization is it's bad for the algorithm if it's changed tracks. But I guess when we translate that into practical terms, wouldn't you want to see students at least from the low track end up in the high track? And that would be a victory from a learning perspective, right?
Yeah, I definitely agree. So I think if I was doing the paper, I would have probably not wanted to consider it always a bad thing. But I can understand that from an accuracy measure, if you think that getting these scores means that this is the right track, and then you change, then I can see how it does at least say it's useful to look at, but I don't necessarily agree that it would be a bad thing for people to change tracks, especially since the goal would be to move people up. And then, and I think about it, it might be the case that they really only looked at moving people down as the rating, and if so, I might have said if people go up, but I think it's only really if you move down is what was counted against it in the prediction. But I have to go back and double check.
But you might be interested in how many people stay low before they get high and who those people are and what they're.
Because it's definitely a case where in one of the past versions, because I was familiar with some of the data, there'd be a decent amount of bouncing around once a student's the skills that they happen to be the ones that were the ones that the professor had tagged as being important. So I think the new system probably gets rid of some of that, where just because your strategy is a little bit different, then you don't get put on the low track.
Good. Other questions? Wake up.
Well, I mean, it was a lot of
lull.
Yeah, it was a bit of a couple complicated things that in the slides I wasn't really able to get into, which is the there's a couple different types of clustering going on, but I think the overall end piece is that there's a set of skills that each student type needs, or that's important for each student type, and then we can use the clustering and then assign people to those clusters in order to say which grouping of skills those students think are important, and then we can move on to, and then we can use those to evaluate whether they should go on the high track or the low track. So that way there's a bit more flexibility in how the students can interact with the system. I think that there could be some issues maybe with some of the instructors, because initially one of the reasons why we use the instructor tagged pieces was because there might be a problem that they really want to solve in only one way, and so that's kind of an open question about is should we push hard on that or not?
Okay, should we move along then?
Yeah. Well, if you have any,
thank you very much.
Yeah.
Thanks for coming and presenting the paper for your colleagues.
Yeah, thank you. And if you have any other questions later, you can contact Behrooz.
Yeah.